Why molecular docking? Because when you use molecular docking, you will be able to see if they can fit inside a pocket. Once you show that it is fitting, then you will find a post or ideal orientation, right? So once you show that it is fitting inside the pocket, you will be able to calculate a score, some kind of binding affinity. And also for the best molecule that you can see showing the score, you can also do interaction analysis to see if they have similar kind of interaction as the original molecule or not, or what are the new interaction if they are showing what kind of new interaction is that. Okay, so based on that, different kind of study you can perform. So imagine that this drug molecule, when you do redocking, so you take this drug molecule, do redocking again. Okay, so probably if the docking is good, it will be able to reproduce the same conformation or same pose as the original one, right? So let's say that if it is able to reproduce the same original post, and also you calculate the score. So like 12 kilocalorie is the predicted binding affinity from your docking score. So if I'm going to dock all these molecules, so what you are going to do is take one molecule, dock it, okay, see if they can bind or not. Okay, if it is binding, you will calculate the score. Okay, so one molecule at a time it will dock, and for the millionth molecule you can dock, or even if you have 10,000 molecules, you can do 10,000 molecules. But let's say if you, when you dock 1 million molecule, let's say you have 100,000 molecules, that is showing you that it can fit inside this pocket. But how do you select? I mean, even 100,000 is, almost impossible to do in vitro or in vivo assay, right? So we have to reduce the number of hits. Okay, so how do you select this? One way to select this is you just, you know uh, list out the molecule which is having the highest score. Okay, so you can take like, from this highest score you can take like 10 molecule or so, or 100 molecule or so, depending on your resources that you have. Okay, or otherwise you can calculate the score of this original drug molecule. If your predicted binding affinity of this original drug molecule is 12 calories, then you would like, or I mean, ideally you will be taking this as a cutoff. Those molecule which is showing lesser predicted binding affinity than this drug molecule, I will just leave it off, and those end of the computational kind of technique. Okay, so there are many techniques. So you can, after doing docking, let's say you got 100 molecules, so you can also do ADMET studies. Okay, so the molecule which is having the highest is to so should be less. So all this condition you have to check for these 100 molecules, and then those that passes this adiabatic conditions or the evaluation, you, let's say 10 molecules are coming, so those out of 10 molecules you can undergo again to see, how tightly they are binding or how stably they are binding by using MD simulation. Okay, you can do MD simulation again, and also you can do a free energy of binding, okay, using MMPBSA or some other methods. Okay, so you can come up to like 5 molecule out of this, and then testing 5 molecules out of 1 million or
हाँ सर
10,000
नई
molecules, it is
कॉल आई
much
है
easier. That's why we use
ठीक है
computational method before
मैं
doing
किसी का हूँ
experimental
मैं ओमान
method.
से
Okay,
टूर
so
गाइड पे वुड यू लाइक टू कॉन्टैक्ट सारा माय ट्रैवल एजेंसी
are you guys
इंडिकेटिव
following?
में ओमान कर दें कहानियाँ मैं हाँ नहीं मैं बिजी है ये वो और मैंने अपना नंबर दे देता यार मेरा पर्सनल नंबर व्हाई यू गिव मी योर पर्सनल नंबर कैन यू हेल्प मी इनक्वायर मैं सॉरी आई एम न्यू हियर आल्सो बिजी विद माय जॉब मैं मेरे की
Okay,
मदद
okay.
कर है बुरी
So
हो
I'll
गई
come back to your questions. Okay, so let me just finish the this theory part, and then before starting the practical, I'll just go through your questions. So if you understand this, let's see different types of docking, which is also important to consider before we do the practical session. So docking, you can classify it into rigid and flexible based on their flexibility. Okay. So rigid docking, when you keep the receptor and the ligand both rigid, you call it as rigid docking. It is very fast. It is used in very high throughput screening, and but this is less accurate. Okay, nowadays we don't use this that much. Another way of docking is if you keep the receptor to be rigid. Okay, you are keeping the receptor to be non-flexible. But if you are keeping the ligand to be flexible, this is called rigid receptor and flexible ligand docking. So it is widely used, and you are keeping the ligand single atoms to be rotatable or flexible. And it is computationally, you can do extensive search, and this is more accurate. So this is what we are going to apply in our demo example. Okay, fine. And then there is also flexible docking. So in the flexible docking, you are keeping the receptor and the ligand both flexible. You can do it in two ways. So first way is to allow the side chains. Okay, remember this is the side chain again of some selected residues at the active site pocket. Okay, you are only allowing the side chains of some of these selected important residues at the active site pocket to be flexible. You are not allowing the backbone atoms of the residues to be flexible. Only the side chain atoms of these selected atoms or selected residues of the active site pocket to be flexible, and also you are making the ligand to be flexible. Okay. So another way you can introduce flexibility is that you allow the backbone atoms also to be flexible. Okay, so whole backbone atoms, flexion atoms, everything. So if you are allowing that, then you are calling this as induced fit docking, right? So again, you can classify docking into blind docking and targeted docking based on the where is the binding site. Okay. So in case of blind docking, you are not sure where is your active site pocket, okay, or where is your pocket where you want to do docking. In that case, you can tell the software, this is my molecule, and with I don't know where is the pocket. So the software, you will tell the software that I do not know where is the pocket. So let's do one thing. You just try to find where are the cavities that this molecule can fit. Okay, so it will just check at the surface, on the surface of this protein or the enzyme, to see where it can fit. So you are not describing the active site pocket. So it will go and see if it can bind at some kind of cavity in the on the surface of this enzyme. Okay, wherever the position of the enzyme, where the cavity is present, right? So knowledge about active site pocket is not there, and computational it is very much demanding because you have to search everywhere, and this is error prone. So let's say you have a cavity here and you did docking, you got some good score algorithm, everything. It's just an algorithm and some kind of score you will calculate, but it should be biologically relevant, right? So if this is supposed to be not the uh, active site pocket, but this is a cavity, there are many cavities in the this I mean any protein or enzyme where it can fit the molecule. Okay, but all the cavities are not active site pocket. So but let's say the actual active site pocket is here, right? So you will do docking and say that if you fit inside this pocket, you got some good results, good score, good pose and all. And when you do experimental essay, since the active site, real active site is here, and the docking you have done is in this pocket, so obviously the results from your experimental essay won't be that much positive, right? So yeah, the chances of getting error is high in this case when you do blind docking, but sometimes you can also get potential binding site. Let's say this you did docking and got some good results, and also the active site, actual active site is here itself, then you might also get the positive result when you do in vitro validation, okay, or in vivo validation. So in that case, we have also predicted a potential binding site, okay. In the case of targeted docking, you have this pocket already known in our demo example where acetylcholine active site pocket is shown, co-crystallized, or the drug molecule inside that pocket, right? So the active site pocket is already known. So you can tell the software that I want to do docking in this particular region where the active site pocket is present. Okay, so in that case, you will be calling as the docking as the targeted docking. So active site pocket is predefined. So once you have this predefined pocket, you can create an enclosure or a grid box. So when you create an enclosure like this, you are telling the software basically to do docking in this region only. Okay, so it will be very much faster because you are not going to look everywhere else, and it will be extensive. Okay, you can do extensive search, and this will be more accurate because you are exactly defining where is the active site pocket, and once you see that the molecule can fit properly inside the pocket and get a good score, the potential of that molecule getting the experimental activity may be higher than this kind of docking procedure, blind docking procedure. Right?
समझ गया राजा भैया को बताना और सीधा पुलिया को पकड़ के अभी क्या देख राजा भाई लोग एक्शन लेगा ना ठीक है ना चढ़ के थाना वाला एक्शन ले लेगा.
So let's see how docking proceeds. Okay, so I'm going to just tell you in a general perspective. Okay, so most of the time the software, they have their own structured way of proceeding. Okay, so they have different search algorithm, and the search is the search technique is different in all the different softwares. Okay, so this is just a general overview. Okay, so I mean it doesn't proceed like this, but this is just an overview, and generally to explain it, this is how we can explain only. Okay, so it's a very simplified form of prediction. Okay, so let's see, ligands are allowed to fit at all possible positions on the binding site with all possible conformations, and many search algorithms are available to perform this task. Okay, so let's say if you have a ligand like this and you are allowing it to be rotatable, this is like one conformer, and let's say this is the second conformer, same molecule with different conformation because you are allowing it to be rotatable, right? And so on, right? Depending on the number of rotatable bonds. So you have a active site pocket. So what you will do is you will take the first conformer and try to see if you can fit at every possible position at the active site pocket. If it can fit, then there will be a post generated here. Okay, and same for the second conformer. You will see if you can fit at every possible position at the active site pocket, and if it can fit, it will generate a post here. Right? So several orientation of poses are generated by the search algorithm inside the binding site. For each pose, a score is given by using a scoring function. Based on the scores, the ligands are ranked and selected for further studies. So these poses, it will be ranked by some kind of scores. These are the scores generated by something called these scoring functions. Okay, so to, it's simple way. You just think that the poses will
अभी सुन
be
रहा है
scored. So scores
तो
means
खाली
they will be given some
प्रीति
kind
यार
of
बोली है ना सामने देवा फोन करके
numbers. Okay, so
पहले
let's
बोल
say
दे
predicted binding affinities.
सबका
So
मोबाइल का
if
नंबर
it
लिखा
is
है
12
सबका
here,
मोबाइल का नंबर लिखा है
maybe
भाभी
it
का
is
सबका
10
मोबाइल
here,
का
then based on this
मोबाइल का नंबर
scores it will be
हाँ
ranked.
तो 10 बजे
Okay,
उसको फोन करना बोलिए
highest
मोबाइल
scoring in the
लगाना
first,
मोबाइल
so
से
you can
रहता है
just take the
मोबाइल
top
से रहता है
scoring and then
मोबाइल से
do a
रहता
further
है
studies.
एक एक
Okay,
गल्ला अक्षर दोनों दुकानदार है
this is a very simple way of telling you that first it has to search the poses where it can fit inside the pocket,
हाँ
then
तो
it will
बोली
do scoring by using a scoring function. Okay, certain types of search algorithm. I'll just mention the name, so I'm not going to explain to you in details. So there is something called systematic search and stochastic search. This is generally used in rigid body docking. It searches the conformations sequentially and takes long time and less practical for more flexible ligands. Okay, so stochastic search method is applied to flexible docking. It uses random sampling and it's relatively faster. Some of the examples are this Monte Carlo method, simulated ending, genetic algorithm, etc. These two are applied in this Autodoc core. Okay, so sometimes you can also use molecular dynamic simulation to see the stability or how the pose is that you generated. Okay, this is for refinement only, not for the initial finding of the poses. Okay.
ठीक है सामने तेरे सामने जान में बात करेंगे ना एक बार कॉल करना मैं छोड़ना अभी को कुछ मत बोला मैं तेरा एक बार फोन करेगा 9:30-10 बजे तो एक बार भाभी से पूछ लेना 9-9:30 बजे
Okay, so it uses statistical potentials. Okay, these are derived from the observation of intermolecular contexts that are identified from the experimental structure database. Okay, so I'm not going to explain again that much. Okay, so just think that they are trying to get some kind of scoring function from experimental database or experimental data by looking at how they are having some kind of frequency of interaction. Okay, so if that particular molecule have atoms have that particular interaction, how frequently they are having some kind of pattern they are looking for, and then based on that they are trying to generate some kind of statistical potential. Okay, so those they are using in the knowledge based scoring function. Okay, so in the empirical based scoring function they are using directly the binding affinity data. Okay, so experimental binding affinity from various data sets. Okay, so and then they are fitting this into theoretical values by creating a model. Okay, some kind of linear regression model. They calibrate this. Okay, and then they use this as the empirical based scoring function. Okay, so this is the equation for calculating the predicted binding affinity. You calculate the van der Waals interaction, see the van der Waals interaction, hydrogen bond interaction between protein and ligand, electrostatic interaction, desolvation effect, and one more thing you should be keeping here, torsional energy also. Okay, right? So let's not go into this in details. So what are the tools we are going to use? MGL tools, and then this comes under Autodoc tools come under this MGL tools, and you have this AutoGrid 4 and Autodoc 4. So when you install Autodoc 4, right? So when you download and install it, you will be getting these two files. Okay, so I'll tell you how to extract this file and use in running in the practical session. Okay, so you should have the receptor and the ligand files, right? So this also will download from PDB database. So what are the file formats that you require? PDB, initial row data, and then we have to convert this into PDB-QT format because Autodoc 4 or any Autodoc program like Vina, they accept the input file in the PDBQT format. Okay, so you also require this grid parameter file for generating the grid map files, and then you will be also creating a grid log files containing all the informations about the grid box and the interaction energies. And you will be again generating a docking parameter file. In this file you will be saving all the information about the algorithm, what kind of algorithm you have chosen, what are the parameters and all. So finally, you will be getting a docking log file. This will contain the score of the docking as well as different poses. Okay. So we have to extract the files and the energy from this final docking log file. Okay, this is the workflow. So you have the protein and you have the ligand. So you have to separate these two. If you have co-crystallized ligand, then you have to remove the protein or ligand from the active site pocket and keep it separate. Okay, receptor separate, ligand separate. So if you have some unnecessary chains, you have to remove them. So I will tell you what is this unnecessary change in the practical session. Okay. Again, you can remove the water molecule, but you should be very cautious because sometimes there are conserved water molecules which plays an important role in the interaction between the protein and the ligand. There can be water mediated interaction between the protein and the ligand. So in those cases, you have to keep those water molecules which is conserved and involved in that kind of activities, right? So then you have to add polar hydrogens and then assign charges. Okay, the same thing for the ligands. You have to add polar hydrogen, assign charges, and you can also tell how many rotatable bonds you should add or remove. Okay, so we'll be using default for this demo. Okay. So once you have processed the receptor and the ligand, you will convert them into PDBQT format. Okay, once you convert the PDBQT format, since we are going to do targeted docking, remember what is targeted docking? We define the active site pocket, right? So in this targeted docking, if you have the ligands receptor here, you'll be telling the software that I want to do docking in these positions where the active site pocket is present. So you have to define a binding site. Okay? You'll be generating a grid box. Once you generate a grid box, you will have a grid map files. Okay? So you produces what? Grid parameter file and grid log file as well as grid map files. Okay, once you generate these files, next thing is to set the parameters, select the algorithms. Okay, so once you select the algorithm, set the parameters, then you will be running the final docking. Okay, that final docking will produce. So this will be the input file, docking parameter file before running the final docking. So you will be generating the final docking file. You can name anything, but the extension should be docking log file. So inside this docking log file, you have this score and also different poses. From that, you can also analyze interaction and do an interaction analysis. Okay, this is the workflow. So let's go to our practical session. Okay. Okay, let me just come to your this thing. Yeah, certificate. Yeah, for 2 days. Certificate is for 2 days. Okay, so if you register for this paid version, then you can. We'll be providing you the certificate for 2-day workshop. Is there any evident difference in the basic understanding between molecular docking and virtual screening? Yes, see, virtual screening is something. Okay, I've hidden actually.
What do you need?
वो दो ट्रेलर गए 36 आई
उसके लिक्विड के
Everyone, can you see the slide? Yeah. So this is like 2D based screening. Okay, so this is like pharmacophore based screening, this is like
कैसे
shape
मतलब
based
उसका
screening, and again this is a
मतलब
screening using molecular
अच्छा
docking.
अच्छा
So all this comes under virtual screening. So what they are trying to do is they are trying to find molecules or hits that can interact with the target. Okay, so even this 2D based screening, pharmacophore based screening, QSR based screening, shape based
यहाँ
screening,
नाइट में
all
कैसे
comes
करता
under
हूँ
virtual
वो
screening.
आयल की
Okay,
नाइट में वो
so docking also comes under
मतलब ये
virtual
वाले टाइप में
screening.
दूसरे मॉर्निंग में लिक्विड का भी कोई नहीं आया
Okay,
कैल्शियम का तो
this
नहीं
for
आया
I mean,
बस
let's not go into this, right? So I hope that you understood
हाँ
the
वो
main point.
नाइट में मेरे ख्याल में आज चले अभी
पहले दो आरटीसी चेक करवाए जो जाने वाले थे वो, फिर स्टोरेज आया।
The
अभी वो
recording
चलेगा
will be
मेरे ख्याल से
shared
ना
with
तो
the
उसका
paid
क्या करते हैं
participants only. Okay.
हाँ वो बर्नर फाइल करती है अभी तो वो उधर से आदमी आए हैं अबू
How
धाबी
we
से ना
know ligand will be
तो
perfectly fit
बर्नर
in
फायर
the active
करेंगे
site based on score.
हाँ
तुम्हें तब भी आता
Yeah, so there will be score and also there will be a
ये
post.
50,000
Okay.
dirham
So
सैलरी
depending
है
on the
तो उसको
post
गाड़ी
and
में क्या
depending on the score, you have to decide.
दूसरी गाड़ी लेके
It's
आया
not like the
अपनी
best
गाड़ी लेके आए
scoring
और दूसरी गाड़ी थी
poses
निसान की पेट्रोल
are the
प्लेटिनियम
one
हाई
which
मॉडल
will give you
ब्लैक कलर
the
की
this thing
अच्छा वाइट में
that kind of
फिर वो और इनके के पास
interaction
ब्लैक
as
भी है
seen in the experimental one.
एक
Okay,
ब्लैक भी है
so
इनके पास
before
वही
doing
पिछली बार लेके
crystallization,
आया था
there are
वो
many
वाइट वाली
studies that were done.
लास्ट गाड़ी है
I'm giving one example, okay, for one particular target.
वो क्या
So
किया
many of the
वो सैलरी आई दिया कंपनी को लॉन्च करने
computational studies were done, but
नहीं तो बोला
it
क्या
was not like
कहते
the
हैं
best
कल सब आएंगे
uh, poses which is having the best score. That was not
क्योंकि
the
वो
pose
लाजम है
that
ना
was
क्योंकि
determined
एक
later
बंदा
by the
कंप्लीट यूज कर रहा है
experimentals
इसका मतलब है उसको
co-crystallization studies and all. Okay, so it depends like how you want to
कैमरे कैमरे हाँ
approach.
हुआ तो
Okay,
तुम
so
सेट करना
if
तो
there
ठीक
is
है
complementary, if there is positive
कल
uh,
वो
functional
बात
group
निकली
present,
हुई
and
है
if there is negative
पता
uh,
है नहीं
विशाल नहीं है यार वो
environment in the
तो
active
ऐसे
site
थोड़ी जॉब
pocket, there
होती
is
है
chances
ये
of
तो ऐसे भी
attraction,
मतलब
right? So
वो
like
जॉब
if there
करनी
is
चाह तो
hydrophobic
आप उसको रख रहे हो
residues present,
तो वो इधर
and
आकर
also there is
ड्यूटी करता है वो
hydrophobic residues
ना होने
present,
की
there are
बराबरी करता है
chances of having hydrophobic interaction. Aromatic ring is there, and
नहीं
if
तो
there
मैच
is
का फिट
nearby aromatic
मिलेंगे
ring
ना
is present in
अगर
the
अकेले हुए तो टीम से
active
बात
site
कर सकते
residue, there are chances of having this
और
pi-pi
जब मैं
interaction
वॉशरूम
or
गया
some
तो
kind
गाड़ी
of
थी वो टाइम
stacking or something,
जब
right?
वॉशरूम से बाहर नहीं
So
कर सकता
those
तो
kind
भूल
of
गया
interaction may be
पर आते ही
present. So
पहले तो वो
we
कैल्शियम नहीं
also
गिरा
would like to
नहीं
do
वो ऊपर गए
interaction
होंगे लैब
नहीं नहीं वो रात को उतर गया ना
analysis.
सीधा
Okay,
आए चप्पल में
so
थे वो
अच्छा
सीधा
अच्छा
आए होंगे और स्नैप
docking
किए
is just kind of
प्लांट में आ गए
you know snapshot of photograph. Okay, so
चलो
from there
हाँ ठीक है
it's very good for screening large databases because it takes less time as compared to other rigorous method as a molecular dynamics simulation. But once you uh, filter out according to your objective or according to a criteria that you are studying. So once you filter out complexes or hits, you can again further do a short MD simulation and then calculate the binding free energy. Okay, you can do using MMGBSA, and that is more the rigorous than the docking. It will contain the dynamic kind of condition that exists in the nature, right, in the system. The docking is just a snapshot. Sometimes you can see the interaction, hydrogen bond interaction, but when you run MD simulation, later on that hydrogen bond interaction might lost because it was not stable at all, right? And the ligand itself might come out of the active site pocket. So like if you want to do some kind of serious research, then after doing docking, we will do MD simulation to check if the result that is found with the docking is reliable or not. Okay. Yeah, score will be automatically generated. Okay, the best score for molecular docking. Yeah. Yeah. So the recording will be accessible for lifetime. Okay. If I have a protein X that interacts with a two long question, okay, so we have tried to make it short so that everyone can understand. But I'll just go through this,
ओ
Anusha.
मेरे को
Okay.
आपकी गाड़ी ना
During
कैल्शियम
virtual
क्लोराइड की तरफ
screening with
खड़ी है हाँ
ligand library, the ligand showing the highest binding affinity, it was found to bind at allosteric site distinct from the site where the drug binds. If the such situation occurs, how can I confirm whether binding at allosteric? Additionally, how can I identify the active site functionality relevant site within the demonstrator? So you see, before doing docking, I always say that it's you need to do a proper background study of your target protein. Okay, so if you do a literature search, okay, if you do a proper study, and if it is very novel, okay, so if you are not able to find anything like what are the functional domain of this particular protein, just you have sequenced it and you just found that protein is very novel, then you can go for some other databases like PFAM and other functional domain prediction family, protein family prediction. So many are there. Through sequence only they will predict, and also through structure they can also predict. Okay. So there are many databases that you can go through and then predict the particular functional domain. Okay. So if a particular protein is, you know, that doing some kind of particular function, already those information are there. Okay, so like if you are, let's say, you have a proteases, so what are the family of protein belonging to that particular protease uh, protein? Okay, and then what are the conserved residues? These are all known. Okay, so these are conserved residues, and which are the conserved residues? These are cysteine based, which are or there are serine based. So catalytic residues and all, they are all known. Okay, so if you go through literature, you will be knowing what are the probable position of that particular residues. Okay, and if you do a multiple sequence alignment, you will get the particular active residues. Okay, comparing with the known family of proteins. But anyway, so if you have an allosteric site and you see that some molecular binding, so from docking you cannot decide. Okay, but if you do MD simulation, you can see binding at that particular site, does it give any conformational changes, so that in the other active site pocket, does it close the pocket or still the pocket is open? So you can do all those studies. Okay, so by doing MD simulation with the bound ligand at the allosteric pocket, you can see the changes in the active site cavity, okay, of the main pocket, right? So based on that, you can do the analysis. Plus Pro is for a protein. So yeah, let me go back to practical session. Otherwise, we won't be able to complete it today. So you see here in the workflow, we need the protein and the ligand, right? So let's take the same example that we have shown you in the demo. Okay. So let's go to PDB. So PDB is the database which contain the experimental structures. Okay, so if you go to PDB, protein data bank, and type here 4EY7, okay, and press enter. 4EY7 is the PDB ID for protein for the enzyme acetylcholinesterase complex with the drug molecule donepezil. Okay, acetylcholinesterase complex with the drug molecule donepezil. Fine. So this is the structure of the molecule. Okay, so there is, I mean, if you type here acetylcholinesterase, there will be list of molecule present. So there are some criteria on how to select the particular structure for docking. So we are not going to do that. So it will take time. So here we are just selecting which we have already, done some criteria, and this particular structure is found to be good for docking. Okay, so we have already pre-selected this. So just type in 4EY7 in the PDB search option here, and then search it, and you will get this structure. Okay, so this structure is human acetylcholinesterase with the drug molecule in the active site pocket, right? So if you scroll down, you have this macromolecular section. In the macromolecular section, we know that this is the acetylcholinesterase, and in the chains you have this chain A and B. Okay, so this is a homodimer. Okay, so this also we know through literature. You can go through this literature. Okay, so if this is a homodimer, that means the chain are of the same residues, identical pocket, identical same that drug molecule is present in the pocket. So either you can take B or A. Okay, so in this demo we are going to remove B and take the chain A. Fine. I hope this is not complicated, right? So we just have to remove chain B because it's the exact thing as the chain A, right? So no need to include both the chains. And if you scroll down again, you see chain C and D. Okay, so see, chain C and D are some kind of glucose moieties. Okay, again, I'm telling you that you need to do a proper background study of your protein that you want to, or the enzyme that you want to study for docking. Okay, so this sugar moieties, we know that it is not biologically relevant for acetylcholinesterase. So simply we can remove this. Probably during crystallization, they might have put this for stability or something. We don't know, but yeah, this is not biologically relevant for the acetylcholinesterase enzyme. So I'm going to remove these chains also. These are unnecessary chains. Okay, so C and D also we are going to remove, and we are going to keep the drug molecule. Okay, in the small molecule section we have this drug molecule, and the ID of the drug molecule donepezil is given as E20 in this case. Okay, E20, and then other small molecules are also present, which is again, this is some kind of sugar moiety and some kind of alcohol, and again nitrate ions. Okay, these are again not biologically relevant in this particular case, so I can just simply remove them. So some cases, in some targets, there are cofactors present, there are metal ion present, which is very important for their activity. In those cases, you have to keep them. Okay, so those are, you have to follow different kind of procedure. So we are just going to show you a simple procedure in this demo. Okay, so yeah, so these are not required, so you just can remove them. Okay, right. So what we have to remove? Everything else except for the ligand and one of the chain. In this case, we are checking this chain A. Okay, so if you understand this, let's download this structure and try to modify the structure or process the structure, right? So you can just go for download files here and then click here, legacy PDB format. Okay, everyone following or not? Okay, I'll try to go slow. Okay, so yeah, please, if you are also trying with me, let me know where you go getting stuck. So if some of you have not joined the WhatsApp group, this is the WhatsApp group. Okay, if you joined here, those who are asking how to get the workshop certificate and all, we will be sharing the information. Okay, PDB format. Okay, so so you have to go here in the download files and then download the PDB format here. Legacy PDB format. Fine. Once you click here, it will be downloaded. And here I have also downloaded file. I'll just copy this. Okay, I'll create a new folder. So this is my folder that I'm going to use. It is in E drive, and this is 29 August docking, right? And then I'll create a new folder here. Call this as day 1. Okay, one more important thing. I mean, it's better to be consistent and and be careful. Okay, so don't, if you are using command prompt, and if you are going to use the path of your
हाँ जी
working folder, so do not keep a space in between when you save, when you name something, okay, in your folder. So day 1, if you keep a space, and if you are going to use command prompt or something later on, there will be a problem when they try to access the path of your folder. Okay, so always remember to keep underscore or something so that there is no space in between. Okay, so I'll just copy the PDB file that I've downloaded. So I've downloaded 3 times. That's why it's showing me 3 here. Okay, 4ey7.pdb. This is the file that I have downloaded from PDB, and I went to download files and just selected this PDB format, right? So after this, it will download automatically. Just copy in your working folder. So kindly create a particular folder where you're going to store the input and output file in this folder only. Okay, otherwise if you store it separately, when you go through the steps, lots of file will be generated and you will get confused, and chances of getting mistakes and errors will be high. Okay, so better to keep everything in one folder. So let's now open Autodoc Tools. So if you install it in the default way, Autodoc Tools shortcut will be present in your desktop, or also you can start it from the start menu. Okay, so Autodoc Tools. So I have used 1.5 version number, Autodoc Tools version number 1.5.6. Most probably yours will be 1.5.7. It's the same thing. Okay, not an issue. In this particular system, I'm using 1.5.6 is much stable than the latest version. Okay, so that's why I'm using this one. So in other system, 1.5.7 was more stable. So yeah, it's a free software, so you have to be very patient when you are using this software. Okay, this is the interface of Autodoc Tools. And now let's import the structure that we have downloaded, right? Protein ligand structure. So in order to import the file, you have to go to the file menu and go to this read molecule. Okay, so it opens in some other directory, right? In some other folder. So my folder is in E drive, 29 August docking, and then day 1, right? This is my structure. Okay, so I have to select this and click open. So every time when I want to open something, and then if I want to generate some new files, I have to navigate to this particular folder again and again. Okay, so I want to avoid this. So I want next time when I open, it should open like file, read molecule, and directly to my working folder. This is some other folder, right? So how we can do is we can set the path of this interface or the tool. Okay, so this is a working folder. If you go to the address bar, just copy this address of your working folder. Go to the working folder, click in the address bar, just copy the path of the working folder. Okay, working folder means the folder where you're going to store the input and output file. all the input and output file. I have copied the path of this folder. Now go to File, Preferences, go to SAT. Okay. So a window appears, right? So in the startup directory, under this startup directory, just select this all and do a Control V. So I have copied the path of my working folder and I just paste it here. Okay. You cannot do a right click and paste. Okay. Here you have to do Control V. After selecting the whatever path there was present before, you just select them all and do a Control V. Okay. And then make this default. Just click the make default button. That's it. And you can just dismiss this window. So now if I open the file, read molecule, it will directly open in my working folder because we have set the part of this particular tool to my working folder. Okay. So all the output file will also be generated in this working folder. Okay. So the chances of getting error later on will be less. Now let's open the file. Select the file, click open. Okay, so this is a wireframe representation of the protein. So now we are not concerned about this representation for now. So what is important is if you look under this current selection option, okay, in this current selection option, in your case, it may be a plus sign here. Okay, so just click the plus sign or the rectangle here, means triangle here. So it will list out the chains, okay, different chains that are present in the protein, okay, in your protein structure. Chain A, we are going to keep it, right? Chain B, we need to remove. Chain C also we need to remove. Chain D also we're going to remove. Remember? Okay. Chain A, B are the same. So I'm going to keep chain A and remove chain B. Chain C and D are some sugar moiety which is not biologically relevant to this particular drug target or the enzyme. Okay, small molecule, this we will remove later. Okay, so for now, we'll remove the chain B. Okay, in order to remove this, we need to select it first. The first columns allows you to select. Okay, select this chain B, select this chain C, and select this chain D. All right. So after selection, you need to manipulate. Manipulate in the sense you need to delete the selected atoms or molecules, right? So if you want to do manipulation of any kind, you need to go to this edit menu. Okay, so under this edit menu, you'll find a option here, delete. Okay, so it's very intuitive. You see, you have selected that. Okay, you have selected the structures that you want to delete. Now, if you want to delete or manipulate anything, you have to go to the edit menu. Under this edit menu, check this delete option. Under this delete option, many options are present. Okay, but what you have to select is delete selected atoms, right? So you are going to delete the selected atoms. So it's very simple. You have to just click here, delete selected atoms, and this is just a warning that it is going to delete and you cannot undo it. So that's okay. Just click continue. Okay, so you have now deleted all the structures or atoms that you have selected. Now only remaining is chain A. So under this chain A also there are small molecules present. So if you click here the triangle, or in your case it will be a plus sign here. So if you click there, this it will expand and show you the amino acid residues, and if you go to the end of this list, okay, So I need to do one more step before this because it will be very confusing because so many water molecules represent. Okay. So what we have to do is after deleting all the chains, let's delete the water molecule also. So if you, I don't know if you can see or not, there are some red dots present here. Okay. So if you remove the this red dots, they represent the water molecule. Okay. So in order to delete these water molecules, again, deleting is also kind of manipulation, right? So if you want to do any manipulation, you have to go to this edit menu, and now you want to delete the water molecules, right? So go for this delete water option. Okay. If you click here delete water option, water molecule will automatically will be deleted from the structure. Fine, water molecule deleted. So the red dots are gone now. Okay, so let's expand this chain A again because some small molecules are present. Okay, we have to delete them. So if you click this triangle or your plus sign, it will expand and show you the amino acid residue. And if you go to the end of this list, you can see that EDO is present. So if you go again to the file here, EDO is some kind of alcohol. Okay, so this also we need to delete. The two EDOs are present, so I'll just select these two EDOs. E20 is the drug molecule. Let's skip the drug molecule for now. Okay, let's delete the EDO. Fine, these are small molecule which is not necessary for our target. Okay, not relevant to our target. So let's delete this the same way. So you have to go to the edit menu because you are going to delete this. Okay, so again under this delete option, you have to select this delete selected atoms, right? Because you already selected the whatever molecule that you want to delete. Then this warning, that's okay. So click continue. So now those two alcohol molecules are also deleted. It's also deleted, right? So only this particular drug molecule and the receptor are remaining. So for now, I just want to save this structure. Okay. So somehow, if you are going to use Autodoc tools or Autodoc 4 or Autodoc Vina, it's very much sure that it will crash. Okay. So yeah, many bugs are present and it will crash. So it's always better to save structure of the processing. Okay, so we have deleted everything, we have processed very nicely. So yeah, it's better to save this so that if it crashes or something, you don't have to start from the beginning. Okay, you can just start from here. You can just import this structure and then start from here itself. So what I will do is I'll save this structure in PDB format. Okay, so go to file, save, and write PDB. File, save, and write PDB. Okay.
और पानी में डाले गए जाल की रस्सी को अपने दांतों से पकड़कर अपनी ओर खींचने लगता है। दूसरी तरफ पानी में पहले से एक आदमी रस्सी को पकड़े रखा था।
Just to avoid confusion, I'm just going to write here ACE, short form of acetylcholinesterase, E20, right? The name of the PDB ID of the ligand, and then I'll say PDB. So only the receptor and the ligand molecules present, and I'm going to save this. Okay. So if you open your working folder, we have this new file ACHE E20, right? So now I can just proceed from this particular step. Okay, so ideally it should be working, but somehow if I continue from this process, it's giving me an error during the PDB-QT file generation of the receptor. Okay, so just to avoid that time lost, I will just exit. I'll just close this particular software and then restart again. Okay, so if I am restarting, it works. So ideally it should be working, but yeah, somehow it's not working. So I'm going to restart. Okay, so don't get confused why I'm restarting. In your computer, it might work, but most of the computer that we have tried, if we continue from this step, it is giving me error during the PDB-QT generation of the receptor. Okay, so just I'm going to restart. So in between, I'm coming to your question. Okay, small molecule you just deleted in this demo considered irrelevant. So Hilary, I already told you that if it is important, such as cofactor present, metal ion present, you have to keep it. Okay, so if sometimes conserved water molecules are also present, so in those cases, the steps that I'm following now, this is the basic steps. So you won't be able to do with these basic steps. You have to do some other. Uh, for that, you have to do a different way of processing the receptor and the ligand. Okay? But you have to keep the cofactors, metal ions, etc. Sometimes you have to keep the heme, uh, that particular group, right? Or some kind of enzyme. So in those cases, you cannot follow this kind of simple procedure that we are doing here. Fatima, already I have mentioned that chain A and B are the same, so you can keep either chain A or B. They are homodimer, so keeping both the chain doesn't make sense. Okay, so you can remove one of the chain and do that. So Mantiram, again, I'll tell you that what you need to keep and what you need to remove. You need to properly do a particular research or background study of your target protein. Okay, so if your target protein is having a kind of a cofactor or something, again metal ion is there, then you need those. Okay, so if you do a literature research, literature studies and all, and even if you go to the particular uh, article for that PDB structure crystallization, they'll be providing all the information, background information. So you can go through that. Okay. How do I identify the right active sites? So there are many tools like for activity prediction. So there is a 7 days workshop starting from 31st, where we will be telling you how to select right structure. And if there is no structure present in the experimental database, how to predict the structures, how to validate the model. And once you get the validated model, since you won't have any co-crystallized ligand, how to predict the pockets. Okay, again, predicting the pockets, just an algorithm. Okay, so it will predict lots of pockets from pocket 1 to 10. So pockets having the highest score doesn't mean that that is the relevant or biologically relevant pocket. So how do you identify a particular biologically relevant pocket? So some criteria are there. You have to go through that. So all those will be taken care of or explained in the 7-day sessions. But now just focus on this particular basic steps. Okay. So this particular session, we are trying to just give you an overview. So once you are able to do this properly, you can, I mean, reading the paper itself or article itself, or even if you go through various YouTube resources, you will be able to understand. Okay. So if you understand or able to do this basic steps first, you will be easily will be able to do other advanced studies. That's why we are just focusing on the overview of the molecular docking now, for now. Okay. And if you want to go for advanced studies, you can go for other articles, look for other YouTube videos or any tutorials, or otherwise you can join our 7 day session also. Okay. So, but better you uh, first do the basic, this kind of steps. All right. So let me just open this again. Right, so we have already deleted everything. If you go through this this thing workflow, we have removed unnecessary chains, remove water. Now we need to add polar hydrogen and assign charges. But before that, let's remove the ligand. Okay, this one. Why I'm removing this ligand? Because you should be separating. So if the ligand is present in the active site pocket, you won't be able to do docking itself. Okay, it will block the entry of new molecule or unknown molecule that you want to see if they can fit inside the pocket or not. Okay, so you have to remove them, do it separately. So protein preparation separate, ligand preparation separate, right? So I'll be removing the ligand from here now. So I hope that you are not confused why I'm removing the ligand. Okay, so I have to keep the pocket empty so that we can see if some other molecule can fit inside this pocket or not. Okay, so let me select this ligand or the drug molecule. So once you select this, I want to delete this, right? So you need to go to the edit menu again. So under this delete option, you'll find this delete selected atoms. Okay, whatever I selected, I want to delete. So you have to go for this option. Fine, and then click continue. Okay. So the next step is what? Add polar hydrogen and then assign charges. Okay. So you have to go to again adding, deleting, assigning charges is manipulation of the structure, right? So whatever manipulation if you want to do, you need to go to the edit menu. So under this edit menu, many options are there. So you try to find where is hydrogen. So here hydrogen option is there. So you want to add hydrogen, right? So you need to click to this add button, right? And then you need to add polar only and keep everything is default and click OK. Right, so polar hydrogen has been added. So the next step is what? Adding the charges or assigning charges. Again, assigning charges is some kind of manipulation, right? So still you need to go to edit menu, find where is the charges button or option. So here is the charges option and there are many options given here. Okay, so first we need to go to this add Coleman charges. Okay, there is also one present called Gastinger. So in their manuscript of Autodoc, they are saying that Coleman charges is optimized for or compatible for macromolecule, right, receptor, enzyme, etc. Okay, so for macromolecule, you can use Coleman charges. Okay, charge has been added, click OK. So for now, we have processed the receptor. So we need to convert this into PDB-QT format, but we cannot do this directly. Okay, so there is a way to do it. So in the subsequent step, we'll be doing the conversion of this PDB-QT format. Okay, so for now, just let's leave the structure here. Okay, so let's focus on the ligand. So in this interface from this workspace, we have already deleted the ligand. Okay, if you expand this and if you go to the end of this list, you won't find the ligand. Okay, so this is the last amino acid residue, so you don't find the ligand here. Okay, so that means we have deleted from this workspace, but it will be present in the file here, right? Receptor and the ligand, we saved it, so it will be present in this file. So we are going to extract the ligand from this file. Okay, so the advantage of saving this receptor and the ligand is that if you save this with the water molecule and all, it will be very confusing because many water molecules will be present. So yeah, now it is concise. You see, it's after the, if you scroll down, after the amino acid ended. Okay, this is the last amino acid, right? 452, 542. After this, it terminates and it starts with a small molecule. Heteroatoms are small molecules, right? So it starts with E20, which is your drug molecule. It's the carbon atom number 1, and this is the X, Y, and Z coordinate of the carbon atom number 1 of your drug molecule. Okay, so like that. The last is this carbon atom number 26. Okay? So you have to copy all the information of the small molecule or the drug molecule, right? So just copy all this till the end of the drug molecule. I started from carbon atom number 1 and carbon atom number 28, right? This is the E20, and just select all the information about this drug molecule, copy it, and open a new file, paste it there, right? After this, you can go to File, Save As, okay, change this normal text file to all types, okay, all types, save as type to all types. I call this as ligand.pdb. You can give any name. I'm just giving this as ligand.pdb. Okay, save this. Then here you have the new file ligand.pdb. Okay, so what basically we have done is we have just extracted the ligand from this receptor ligand complex. Okay, so once we extracted the ligand, let's import the ligand in this workspace. Okay, then we can hide this receptor for now. It doesn't matter, okay, you hide or you show it, it doesn't matter, okay. For now, let's just hide this. So I'm going to import the ligand from the my working folder. Okay, so this is the ligand. So you can go from this file option, or otherwise, I mean, let's go from here. Okay, so file, read molecule, and then ligand. Open this. So this is our ligand that we extracted, and then go for this. Okay, the third one. So first row, second row, and the third row. We have this ligand menu here. Not from here. Okay. So once you open this in the workspace, you go for this ligand menu and then go to input and go for this choose option. Okay. If you haven't opened this in previously with this one, okay, then you have to go to ligand directly, input and click open, and you have to navigate to the file or folder where this ligand is present. But since we have already opened this in our workspace, we go to input and go for this choose option. Okay, and then in this window, ligand is listed, so we select the ligand and then click select molecule for Autodock. So what it will do is it will add the charges automatically. So you have this Castinger charges added, and it's showing that 15 aromatic carbons are present, and it also detected 6 rotatable bonds, and the torsional degree of freedom is set to 6. You can change this. So sometimes you have Autodoc 4 allows like 32 rotatable bonds. Okay, so it's very difficult to do 32 if you have 15 or 16 or 17 rotatable bonds, and you need to do a lot of increase the docking run. This will talk later on. So you can do a changes in the number of rotatable bond. For now, let's keep the default. Okay, so let's not mess it up. So let's keep the default and click OK. Fine. Now go again to the ligand option here and go for this output. Okay, and then go for this save as PDBQT. Okay, so we are in the day 1 folder. That is our working folder. Many files are there, but save as type is PDBQT format. That's why all the files are not visible. Only the PDBQT file will be visible anyway. So the ligand file from PDB, we are going to save it into PDBQT format. Just click save. And if you go to our working folder, we can see a new file generated ligand.pdbqt. Okay. So if you do not generate this PDBQT format and go through the steps further, you will create problem later on. Okay. So have to go through this output and save as PDBQT. So what is the next step? We have processed the receptor. We have processed the ligand. So the next step is what? Okay, this we have done. Okay, ligand.pdbqt, receptor.pdbqt we have not done yet. Next thing is to generate a grid box. Grid box in the sense we have to define the enclosure where we should be doing docking around the active site pocket. Okay, so if you see here, this is the experimental structure, right? This is representation, but it is exactly how it is, like this one. Okay, so this is not predicted, but it's determined, experimentally determined structure. So the Donephysium fits perfectly into this channel, right? And what we are going to do now is we are going to define a grid box surrounding this particular pocket. Okay, so in the grid box there will be a grid center. That means the center of the grid box. Okay, so it will start generating the grid box from the center. Okay, if we can keep the center of the grid box around here, okay, in the length, in the center part of this particular this what you call this channel, okay, active site channel. Okay, if we can keep the center of the grid box here and then enclose the whole active site pocket, if you increase the dimension of the grid box, it will be able to completely enclose the active site pocket. Okay, so that is the main idea that we are going to do next, then we are going to do in the next step. So where we can tell, like, where is the coordinate to put the grid box center. Okay, so there should be some coordinate, right? So we cannot just randomly or manually do that, right? So what we can do is, for this particular example, since the drug molecule is spanning the whole the channel, okay, from starting of the channel to the end of the channel, right? So if you can calculate the centroid or the middle portion or the middle point of this particular drug molecule, we can keep that as the center of the channel. Okay, that means if we can keep the grid box center here in the centroid of this particular ligand, we can start the grid box from here, and then we will be able to enclose the active site pocket properly. Okay, that should be a proper way of enclosing. All right, so what we are going to do is, I hope that you got the point that I'm saying. Okay, If you do not know, please let me know. Okay, so the next thing is to place a grid box somewhere here, okay? So manually we can do, but it is not proper and it's not recommended. Okay, when you try to do it next time, I mean, you can try with the manual and you can calculate the centroid of this ligand and place the grid box and see the results, see the difference in the results. Okay, so yeah, so grid box also plays a very important role in the results of the docking. So it's always important to place the grid box properly. And whenever I do docking, I'll try to avoid this blind docking, okay? So what we can do is we just open the ligand in any text editor. So, sorry. So if you can calculate, this is C, this is the X coordinate, Y coordinate and Z coordinate of this carbon atom number 1. This is the coordinate in the space, right? So this is same for the carbon atom number 2. And so for the, so and so forth for this carbon atom number 28, right? So this is the X, Y and Z. Okay, so if you can get the average of this X coordinate, Y coordinate and Z coordinate, you will get a centroid or the middle point of this particular molecule. Okay, so those X, Y, Z coordinate or the centroid, we can place it in the grid box center, or the grid box center can be placed in that centroid. Okay, I'll show you what I'm trying to say here. Okay, so let's calculate the centroid first. Sorry, copy. Let's select them all and then copy, and we can use Excel for this. Paste it here. It's not properly formatted, so you can go to data, text column, next. Yeah, some kind of space are there, I think. So it's properly formatted now. So we need to calculate the average of this X coordinates of this particular, and then G coordinate, X coordinate, Y coordinate, and Z coordinate, right? So if you want to calculate the average, what you can do is go to home again, and then under this auto sum function, you have this average, okay? Average option. You go press the average and press enter here, okay? After selection, you just press enter. You get the average of this particular column. And then if you drag this, you'll get the X, Y, G coordinate. I'm not doing any fancy thing, okay? Just calculating the average. Summation of this divided by number of this particular atoms. Okay, that is what we are doing. So minus 40, minus 43 and 27. These are the centroid of this particular drug molecule. Okay, so we'll be placing the grid box center in this centroid position. Now let's start to generate the grid box. Okay, so before we generate the grid box, we have to tell the software that this is the macromolecule that I want to use for grid box generation, and this is the ligand that I want to use for that grid box generation. I mean, don't take this as like you cannot write like this in exam. Okay, there is a reason why we are giving the macromolecule and the ligand again, just to make you, or just to simplify, I'm telling. Okay, so here go to grid menu here, and here you have to say that macromolecule which I want to use for generating the grid box. Okay, so macromolecule, since the macromolecules are open here, I'll go for this choose option and then select the macromolecule from the window and then click select molecule. Fine, and just click OK, and now you will be able to save the receptor in the PDB-QT format. So I'll just call this as process ACHE only, right? And then PDB-QT. So if you open the folder again, you are able to see. So for ligand, you can directly say from here output and PDB-QT, but for the receptor, there's a kind of different way to save this. You have to go to the grid, macromolecule, whatever, if it is open, you have to just choose, go to the choose, okay, and then after that you will be able to save the structure, PDB structure of the receptor in PDB-QT format. But for now, the procedure was to generate the grid box. So in order to generate the grid box, we have to define the macromolecule and also the ligand. So we have already defined the macromolecule. So for the ligand, you go to the shape map types and go for this choose ligand, because already the ligand is also open in the workspace. So you go to the choose ligand, and from the window listed is the ligand here. Select ligand and then click the select ligand button. So ligand also selected, macromolecule also selected. Again, go to the grid menu. Now you go to the grid box. Okay, so it's something like this. So what you can do is you can change, this is center of the grid box, okay? This is the center. So you can change the position of the grid box. Manually, you can try to locate where the active site pocket is and try to place the grid box. But this won't be proper, okay? No matter how much you try, this won't be a proper way to place the grid box. Okay, so remember that we calculated this one. So the grid box position will also be changing, okay? You see, minus 14.1085. So we'll be placing the grid box the center part of the or the centroid of the ligand, okay? So here, if you type here minus 14.10, okay, and then in the Y center minus 43.83, 27.66, 27.66. Right. So now you can see there's yellow star here. No, this is the center of the grid box, and now we have placed exactly at the centroid of the ligand. So now I can see that ligand that is present, which spans the whole channel of the active site pocket, is now covered with this grid box. So what this grid box will do is you will do docking in this particular region only, so it won't go outside of this grid box. Okay, so it is important to completely cover the active site pocket. Fine. So you can change the dimension of the grid box also, but if you change the dimension, obviously you will increase the computational power, and also the search space will become larger, okay? And depending on how many runs you give, the results also will be different. But anyway, let's give the default for now and see. So these are the small parameters, but it becomes very important. So which parameter that you have entered here will give you the best kind of docking results that you have to also see, and for that you have to validate the docking procedure, okay? procedure in sense, what are the parameters or what are the options that you have used to do the docking. Okay. So later on, we'll
नहीं
also
ये
validate the
कभी
docking protocol. So
150 ओवरफ्लो कर देते
at
हैं,
that
कभी
time, I will
170 ओवरफ्लो
explain
कर
to
देते
you how
हैं,
to validate.
कभी 110 ओवरफ्लो कर देते हैं.
Now we have placed the grid box properly, and then all this data that we have entered, we have
नहीं
to
दो बार
save this
ये
for the
बुझाते
next
क्यों
run.
नहीं
Okay.
हो? अभी जो
So
माने जो
in order to
है
save
सैंडोज
this
वाला,
in this window, you have to
वो
go to
क्या
the
उसकी
file
डीपी है ना साहब, वो
and
कहते हैं
click here
सैंडोज
save
वालों की ड्यूटी होती है
close
कोड
saving
जीएस वाले
current.
बस कोड
If you
करे
do not
रहना
do
है.
this, the data won't be saved and you
वो
will
कब
not be
करता
able
है?
to do the next step properly. Okay. So
नहीं वो स्क्रैप
close
के लिए
saving
थोड़ी
current, click
होता
the
है.
close saving current,
नहीं नहीं सैंडोज वाला
right?
हटता है
And
तो
then
साथ में
go
बैठने
again
के
to
लिए
the
थोड़ी
grid
शिफ्ट इंचार्ज
menu.
है, 3 लोग हैं, ये
And
एक
in
होने पर
this
डिस्टेंस वाला जो
output
है
option, you will
सारा
be able to
उसी को
save the
उसके
grid
ऊपर थोपा
parameter
हुआ है कि
file.
भाई तुम
So in
डीसी
the
कर
grid
देता
parameter file,
और तुम
all
जानो
this
तुम्हारा काम है.
uh, data we have entered will be present. Okay, so I'll just call this as grid.gpf.
हाँ
Okay,
वो
you
उससे
can
तो
keep
लाजम है,
any
एक
name,
आदमी होगा तो
but
कुछ
the
ना कुछ तो
extension
मिस्टेक
should
होगी
be
उससे.
grid parameter file. Okay, gpf file. Save this, and if you again go to the this working folder, we can see that we have generated the grid parameter file here.
हाँ ये तो है, लोड फुल चल रहा है ना बस ठीक.
Okay, so now we have to run a program. So to run a program to generate grid map files, okay, we need the .ext file. Okay, so we need to go to this run menu here and then go for this run auto grid. So this is the input file for generating the grid map files and the grid log files. Okay, again the name itself is telling you that this is a parameter file, that is the input file. Okay, so grid parameter file. So when you run this, you will be generating a grid map files and also a grid log files which contain all the information. Okay, so to run this, we require that AutoGrid 4.exe file. So in our working folder, we do not have that currently. Okay, so let's collect the file, that .exe files. So when you install the Autodoc 4, if you follow the default option, we will be installed in this program file 86, and then the Scripps Research Institute, and under this you have this Autodoc and then version, and you have these two files. Okay, these two files we will require it for the final grid map generation and the final docking. Okay, once you copy this, let's come back to our working folder and paste it there. Okay, so when you install the Autodoc 4, okay, so you will be installing, I mean, if you use the default path, if you do not change anything and just have to click yes, yes, okay, or the whatever the default option that they have given, it will be installed in this program file 86, the Scripps Research Institute, Autodoc and version, and these two files will be present. Just copy these two files, come back to your working folder and paste it there. Okay, so once you paste it there, now you can use this file to run the the grid map generation. Okay, so for that, the next step is to generate grid map files. So for that, you have to go through this run menu, click this auto grid, run auto grid, and then in this program path, you have to navigate to the file, that is this file, autogrid4.exe file. This is the executable file. And also you have to give the full path of this grid parameter file. Okay, so here again, this is in our working folder. Okay, so just open this, fine, and grid.glg will be the output file. Okay, so once you have this all, remember the autogrid4.exe file should be there in the same folder. the grid parameter file should be there in the same folder, and the output file will be generated in the same folder. Okay, so click the launch button here. So it's running, and if you go to this file, so grid map files are generated, and also the grid log files also generated. So we have completed the generation of the grid map files. Okay, so the next step is to set the parameters for our docking. So we have to select the docking algorithm, set the parameters of the docking algorithm, and then again run the final docking. Okay, so to again the same procedure. So for grid also, we tell the software that this is our macromolecule, this is the ligand that we want to generate the grid map files for. Similarly, you have here is the final docking menu. Okay, so here we again are going to tell the software that this is our macromolecule, and we are doing the rigid docking. Remember, the receptor, we are keeping this as rigid and the ligand as flexible. So you have to tell the software that the receptor that we are going to do is the rigid docking that we are going to do. So we have to select rigid file name. Okay, that is our macromolecule, this one, PGBQT format. Click open, and again go to docking. Now we'll tell the ligand, tell that this is our ligand that you want to dock. So ligand is still open in the workspace, so I'll go for choose option. Ligand is listed here. Select the ligand and click the select ligand option. Okay, so some parameters are there, so let's not change this. Let's just keep random and click accept. Okay, again go to docking, and here the option to select the algorithms are present. Okay, so you can have this genetic algorithms, mail channeling, local source parameters and all. So anyway, so let's select the genetic algorithm. So if you read their manuscript or their article, original article for this particular Autodoc 4, it is described there that genetic algorithm gives the kind of best docking results. Okay, so let's select this one, and you have this genetic algorithm parameters. Okay, so yeah, so you can do changes here. For now, let's not do it. So you need to understand what are all these conditions. So before that, let's not play around. Okay, so yeah, so let's keep the default and just click the accept button. Okay, again go to docking, and we have selected the genetic algorithm. Inside this genetic algorithms, there were many parameters. We are keeping that as default, and after that selection, we are going to save the output. Okay, this output will be the input for the next docking run. Okay, so let's select the Lamarckian genetic algorithm. So this seems to be best. So we'll call this any name you can give. So I'm calling this as doc.dpf. Okay, docking parameter file. So should end in the this extension. Okay, save. And if you see the folder, working folder here, you can see that docking parameter file is there. So let's run that. Okay, similarly, this will be the final run. So similarly, we have to go to this run menu here. And then previously we did this for grid map generation, and for final docking, we have to go for this run Autodoc option. Okay, click this run Autodoc option. And same as before, we have to browse or select the part where the this autodoc4.exe file is there. So just select them, click open, and also the full path where the DPF file is there. Okay, browse doc.dpf, click open. Okay, keep everything as default and click launch. So it will run and give you the docking that log file, okay, DLG file. Now nothing is there, 0, because it is still processing. Once it is done, some size will be there. That means all the information will be there. Okay, poses will be there, and also the binding affinity, predicted binding affinity will be present. Okay, let it run. So let me see what you have. I hope that you have opted for that. I mean, yeah. So I repeat again, then it will be very confusing now. Arun Kumar, what you are asking? Why are we removing water molecules and water? How do we know what is the receptor in the presence of this molecule and what? I'm not getting what you're asking. Okay, so if you are asking like what is the contribution of water and if there is any contribution of water. So in docking, there is no explicit or implicit model present to calculate the water presence, okay? So there is desolvation effect, but it doesn't give you the whole picture. So that's why we do MD simulation where explicit water models are present and to see if the condition that is really there in the system are also exists when we do MD simulation, okay? So yeah, so but sometimes when the water molecules are conserved, we keep it there, okay? But it doesn't count as the kind of that uh, the effect of water, okay? So it's different. So contribution of water, if you can keep in the algorithm, but it is not there in case of the stocking and all. But yeah, some kind of contribution is there, desolvation effect is there, but it doesn't model the water explicitly, okay? So that's why we are removing the water, because it will be some kind of dummy atoms present. It doesn't kind of contribute to the docking condition. So sometimes it will block the ligand also. So unnecessarily we will be calculating the if the water is present, unnecessarily we'll be also calculating the presence of water, but it doesn't contribute to the final kind of score, okay? Yeah, for I'm already have told you that we are having the this tutorial in PDF. Whatever we have done here, the same process is explained here step by step with detailed explanation. So you can follow this particular tutorial, and also, I mean, you can see the video for reference and follow the steps at your own pace. Okay, so one time docking, if you do practice, it won't come. I guarantee you it won't come. Okay, so you have to practice again and again, and there will be some silly mistake you will be making. But if you keep on trying and if you keep on looking at this tutorial and follow the videos, I'm sure that you will be able to do the final step. Okay. Of course, those who are not opted for this tutorial and then recorded video, please join next time also so that you can also see that. So we are coming to the validation of the docking results. Okay. All right. So I think the docking is done. Okay, here is the DLG file. Yeah, it's 70 KB, 79 KB, right? So if you just open this, and if you scroll down, you'll find a table here. Okay, so this gives you the binding affinity. Okay, so remember, I don't want to confuse you, but yeah, just when you select this docking and then algorithm, here in the genetic algorithm parameters, genetic algorithm run is 10. Okay, so if you give 100, then it will generate 100 runs. Okay, so 100 conformers will be generated. So we have just done 10 runs, so 10 runs are done. The run number 3 or conformer number 3 is having the highest binding affinity. Okay, fine. So let's see how is the results. Okay, we'll extract or see the interaction, how it is as compared to the original structure of the ligand or the molecule. Okay, so there is one more concept. Okay, let me just tell you this one quickly. So how do we know that the docking that we have done is correct? Okay, so let's say that this is the ligand at your active site pocket. This is the co-crystallized ligand. Okay, or the drug molecule at the or the active site pocket. This is experimental. Okay, you know that in real system also this pose is existing. Okay, so when you remove this or when you extract this ligand or the molecule, the drug molecule, and then you do redocking. Okay, if the redocking can produce the same kind of post, same kind of pose as the original or experimental structure, that means your computational simulation is able to generate the experimental kind of conformation. That means your docking setup that we have done is correct. Okay, that means you are able to create the same kind of condition that exists in nature, right, in the real system. By looking at this, you can say that, okay, this is similar. Okay, how similar? If you're asking how similar, we do not know. Okay, so even if you show similarity, there is some cutoff. Okay, so if you have 2.5 angstrom or 2 angstrom, okay, the RMSD, that is root mean square deviation between the heavy atoms of this original conformation and the dock conformation. Okay, If it is above 2.5, we do not consider the docking procedure that you followed is good, okay, or acceptable. But if it is below 2.5 angstrom, okay, then we consider them as a acceptable docking protocol. That means your docking simulation is able to generate a conformation or post or ideal post similar to the original experimental post. Okay, that means your docking protocol is working. Okay, now you can use the same protocol in the sense how we set up the grid box, how we did the charges, okay, how we did the algorithm selection. There are parameters present in the algorithm. So in the advanced study, we will be changing those parameters if some kind of this docking validation satisfaction is not there. Okay, so that we not going to cover here. So all those are called as the docking protocols or docking setups. So if your RMSD value between the original and the dock conformation is below 2.5, then you can use the same setup now to dock unknown ligands, okay, from the database, okay, from the ligand library database. So if you see any paper, you pick up any paper of docking, and there will be this docking validation if there is Cox's structure, okay. There will be docking validation protocol. In that, they will be calculating the RMSD. So if the RMSD is below 2.5 angstrom, your docking protocol is considered to be acceptable. Is this understood, everyone? Are you following? Okay, so let's calculate the RMSD value and see how good is our docking. Right? So we got the .dlg file here. So we need to import the .dlg file or open the .dlg file. To do that, we need to go to the Analyze menu, Docking, and click Open. Okay, I'll repeat again. Go to Analyzed, Dockings, and click Open. Okay, so the DLG file is there in the same working folder. So select the DLG file, click Open. So you can change the name of this ligand. Okay, so it doesn't matter, but let's call this as docked. Okay, that's okay. You just click OK. Now I want to see the different conformations. Okay, so if I go to Analyze again, go to Conformation, and then click Play. See, this is the first conformation. Okay, first conformation. I'll just hide the receptor. Okay, so it's better now. The green one is the original conformation of the ligand. So docking number 1 or conformation number 1 is quite different from the original post. Okay, and if you open the score, you see docking run number 3 is giving you the highest score. Okay, let's see if this run number 3 is giving you a better pose or not. 2, okay. Yeah, 2 is also almost similar to the docking original post. 3, okay. 3 is something like this. And if you again see here, almost like same kind of not that much different. Okay, this scores binding affinity. And if you can see here the clustering, okay, if you see here it's saying that 9 cluster of the same conformation are present, only 1 is different. So most probably this one will be the one which is quite different. And if you all put all the conformation here, then it will be kind of similar conformation. Okay, so that means the possibility of having that particular conformation, okay, or the real conformation maybe this one, okay, with the cluster number 9. That means 9 conformation are present in this cluster, okay, and in cluster number 1 only one cluster is present. So the run number 3 with the highest among this cluster, okay, highest binding affinity among this cluster is this one. So yeah, so only this one is there. So out of the 10 run that we have generated, 9 are having same poses and only one is having a different pose. Okay, so highest binding affinity in this cluster is run number 3, and which is the representative structure of this cluster. Okay, so let's take run number 3. Okay, almost the same cluster. See, same conformation. Only the one is having a different kind of conformation here. So from this also we can see which is the dominant kind of post, okay, depending on the cluster. So most probably the cluster with the highest number of poses, generally, I mean, ideally maybe the one which can have those kind of poses which is stable, okay, but it doesn't tell you all the time like that. So best thing is to just after doing docking, do a quick MD simulation, 100 NS or something, to see if the structure is really stable in the active site pocket or not. So docking alone is not enough. Okay. Right. So let's extract this pose. Okay. Let's extract this pose and calculate the RMSD value. So to extract this pose, we have to go to this ampersand button here. Okay. So there are many options to play around. So learn or play around with your own time. Okay. So we won't be able to do it here. So just click here. Where is that? Write all. Okay. So write all. If you do, all the poses will be extracted. Okay. So currently, what is there is that in the doc.dlg file, all the poses are there. Okay. The 10 poses. So if I do write all the poses in PDB-QT format separately will be extracted. Okay, 1 to 10 or from 0 to 9, okay, depending on the numbering that you are going to get. So if I click here, write all, you will be getting new files. See, doc confor 0 PDB-QT, doc confor 9.pdbqt. It started from 0. So our best docking score was this confor 2, right? So 0, 1, 2 means 1, 2, 3, third conformations, right? Third run. This one. So in this case will be the confor 2.pdbqt because it's starting from 0, right? So let's calculate the RMSD between this one and the original ligand, right? The ligand.pdbqt. For this to calculate, we'll be using a easy kind of web server. Okay, so it is called doc RMSD. Here you have to input or browse the file in mol2 format. Here original and the doc post, original post and a doc post. Okay, so they require in mol2 format. So we have in PDB-QT format. So we need to change this, right? The format. So if you want to change this in PDB-QT to mol2 format, we can use OpenBubble, but you also have, command prompt way to do the conversion as well as graphical user interface is there. But let's go for command prompt because graphical user interface, it's kind of many things we have to do. Okay, so here in the in your working folder, let's click to the address bar and type here CMD. Okay, just type here CMD and press enter. You will get a command prompt, and now it's pointed to your or inside your working folder day one. Okay, otherwise you can open from here also CMD, and this is in different path. Okay, so you have to navigate to the path. So leave this one. I repeat again, if you go to this your working folder address bar and type here CMD and press enter in your keyboard, you'll get a new command prompt, and it's there in your working folder. Okay, so you can access all the files. So if you type here O Babel, so O Babel, so remember the files that we have given you. So Open Babel is the one for conversion. Okay, if you install Open Babel properly, you will be able to use this O Babel from the command prompt. Okay, so in the command prompt, you type here O Babel, which is one of the module present in Open Babel. Okay, so O Babel space the input file that you want to convert. Okay, so let's convert the doc confirmation first. Doc confo conf to dot etbqt, right? And then space minus capital letter O. Okay, you have to keep capital letter O, and then space again, and the output file that you want to generate. Okay, so you can give any name for this. I will give as doc confo. Actually, it was 3 and it was the top scoring, right? So it was in Mol2 format. We need to convert. Okay, very easy. Open Babel, from Open Babel, you have this O Babel module, then give a space, the input file, that means the file that you want to convert the format, and then space minus capital O space and the output file. That's it, in the format that you want to convert. So one molecule converted, right? So if you can see here, doc confo 3 top.2. This is the output file name that I've given. So for the doc compound, we have converted. The confirmation we have converted. Now let's do same for the original ligand in Mol2 format, right? So O Babel, what was that ligand? You can do PDB-QT, PDB, the same thing. So this is the input file minus capital O and the output file. Okay, I'll just keep the same name because it will be in Mol2, so we can distinguish easily. Okay, so press enter. One molecule also converted, and you can see here ligand dot Mol2 and doc confo 3 top Mol2. Fine. So we'll browse the files here. Here day one, and then the original confirmation in Mol2 format, right? And this one doc confirmation in Mol2 format. Open. You can keep everything as default and just click run doc RMSD. Yeah, so the calculated docking RMSD is 0.626, which is way below 2 angstrom. So now you can use the same grid size, same selection of the algorithm, same parameter that we use in the algorithm, and then do docking for other known ligands. Fine.
You can ऊपर नहीं आना. ले.
Okay, so let me just quickly show you how to visualize this, okay, in different software. Then we'll wrap it up, and tomorrow those who are going to join or those who haven't joined also, you are welcome to join, okay? So please, if you are not in the WhatsApp group, please join there, and all the information will be provided in the WhatsApp group. So if you open Chimera X, the good thing about Chimera X is it also accept the PDB-QT format, so you don't have to worry about the PDB-QT format. So click here, File, Open, and then go to this day one process. Where is that? Yeah, this is the receptor only.
नहीं
And let's open the ligand
कंप्यूटर 'ਚ सेट किया ना तो उन्होंने करांगा रिड्यूस करांगा
here. Okay. You can change the background. And there are many different ways for representation you can play around, okay? So I
ऑडियो
won't be
करना
going through that. So if you want to see hydrogen bond kind of
उनका नहीं
interaction, you
करना
just
का
need to select the molecule first, the ligand molecule first. So go to select residues, and then so it is given as UNL, okay? So after docking, they have changed the name to UNL. So it's okay. So you just go to residues, UNL, it's selected, and then there will be this hydrogen bond here, okay? In molecular display option, in the molecular display window, you'll have this hydrogen bond option. You click here. If there is any hydrogen bond, you will see these dotted lines, okay? This one. Yeah. So tomorrow in Discovery Studio, here we cannot see the pi-pi interaction, all those important or interactions, okay? Pi-pi interactions, cation pi interaction and
ये
all.
तो सॉफ्टवेयर है
It's not,
सॉफ्टवेयर है
maybe I'm not able to find it, but in Chimera, I have read the manuals also, but we are not able to find the to show that in 3D, okay? The pi-pi interaction and all. So in Discovery Studio or in Mastro, we can see that interaction. So tomorrow what we'll do is we'll show something like this, but we also will create the figure, okay? Something similar to this. So this immediately this can be used for publication, right? So something like this we'll show in Discovery Studio today, tomorrow. Okay, everyone. So I'll go through your question quickly and then we'll wrap it up. Man interaction or that hydrogen bond interaction, that pi-pi interaction, van der Waals interaction, etc. Okay, hydrophobic interaction and so in simulation we show high affinity of the drug with the receptor, but in vitro when we check the drug on live cells, water molecules affect the affinity of the ligand. So Arun, I again will tell you that docking doesn't give you that kind of results, okay? So docking won't give you a reliable results. So in many of the docking, this paper from their software, okay, they will show correlation with some data sets, okay. But if you try in different data set, you won't find it predicted binding affinity versus the experimental activity. You won't find that correlation, okay. So yeah, that is there. But if you do rigorous kind of MD simulation, and MD simulation is not absolute, okay, it's also just a prediction, but it also give you the real kind of environment. So water is also present. If this water is there, I mean, explicit water molecule will also be present. And then, if the membrane is also involved, then you should also include the membrane, because that's the anchoring point. If you remove the anchoring point, the changes that you're going to get without the membrane bilayer, it will be different. So we try to at least mimic the condition that exists in the real system. Okay, but it doesn't give you, it's not every time when you do it, it won't give you the absolute kind of correct kind of results. Okay, so yeah, so that's why we do list of molecules. So because we are not so sure that that will be the one that will give you binding affinity. But yeah, instead of doing millions of molecules or tens of thousands of molecules, you can come down to at least 100 or so molecule, and then do that. Okay, instead of doing thousands of molecules. Yeah, multi-ligand docking is possible in Autodock, but it requires so many manipulation. Okay, scripting is required for that, but yeah, it takes time. Okay, everyone, thank you so much. We'll see you tomorrow. We are going to do multi-ligand docking and library generation, and then after doing docking, we'll generate a nice publication-ready figures. Okay. Thank you, Fatim. Thank you, Amis. So we'll be sending you the recorded video for the paid participants before 12 p.m. tomorrow. Okay. So Indian Standard Time. Okay. Thank you. Thank you all. Thank you all. See you tomorrow. Okay. Bye-bye.
लगता खत्म हो गई